lower down. So. I can do it. Make sure you get the driver. Okay. Let's see if you can get Brian on our team. He just gives a thumbs up. You weren't hit about skin. That didn't do your eyes. It's from Jeff. Yeah, we got a scanner. He's scanning. He can sit on the one. So should. Just walk around or something. We can do that. Scanning stuff. Hello, everybody. We've never been here before. Welcome to Sector 67. We do these monthly meetings. People give project presentations or talks or whatnot. So Davie's gonna come to us live from his garage, and then we've got a couple of presenters in person here. So, Davie, you want to take it away?
Hi. Can you guys see and hear me and all that? Okay.
Yep. Yeah, you're in good shape.
Like any good project, this started with an easy enough ask from my wife. I don't know, to fill you guys in on what I've been doing with my life. A while back, my wife brought me home 70 of these, I think, which it looks like it's rusted steel, but it's actually solid brass at almost 2 inches in diameter, almost 3 feet long, which was pretty sweet. So naturally, she wanted something in return. Among her asks were a chess set. And so if you watch my horse video a while back or the night, you might recall that I made a pawn, right? So I did a pawn. And then Chris was like, well, great. Who cares? Everybody does a pawn. Do something fun. So then I did a horse. And yet no one was impressed. So now I had to finish out the set. So I've been working diligently on this, and I got quite stymied by the queen. And one of the benefits of this is that I'm not actually doing design work. I'm just following, because she has this marble chess set. So I'm just trying to replicate one of the pieces so she can play white or green marble against this new brass set. So here is the queen, and I'll go ahead and share my screen and show you I've got a short slideshow here. So give me a second. I'll just do the whole screen and you'll see. So you should see this chess piece now on my screen. And so this is the kind of marble variant of what I need to produce out of brass. It seemed like a really neat idea until I figured out. So I went over into Fusion. Can you guys see my Fusion screen now?
Yep.
Okay. So I went into Fusion and drew it all up. And then this is where everything got weird. So side profile work, totally cool. Everybody understands that. That's just normal kind of turning on a lathe. However, to scoop out this center here with this ridge, with the kind of nipple in the middle and kind of scoop all this out is called face turning, which apparently is super taboo. in in machining. It's not taboo necessarily. People just avoid it at all costs. And I've learned why. My coworker who's a machinist even said, yeah, my coworker is a machinist and even said, everybody avoids that. I don't know why. It's just, most people try to go with a lollipop cutter. And then he looked at this and he goes, you should use a lollipop cutter. So by that, he meant, if you can, I'll stop sharing for a hot second so you can see my screen. This is just a random, whatever piece of plastic that I have. But a lollipop cutter in a mill would come down like this, and it's shaped like a lollipop on a stick. And you would just use it in a 4th axis and rotate it around on a regular mill while you're cutting. That didn't sound fun. Lollipop cutters are like $100. They do make proper tools to do what I'm asking, also several $100s. For a one-off part, I really didn't feel like spending the money, and I didn't really feel like it was in the interest of the sector community to just buy my way out of a problem. So instead, I chose to spend dozens, hundreds, thousands of hours on this, many hours of thought, many hours of research, no money really spent except for one lathe tool that was pretty cheap. And so anyway, let me go back to sharing my screen. Sorry, I'm a little, I do this all day long, and then I come here and I feel like I'm 100 years old all of a sudden. So let me show you kind of this thing here. So there's that. We just talked about that. So the problem with face grooving with a normal tool, and I'll grab kind of a regular old, it's in the lathe right now. But when you have a regular tool, you need this relief underneath the cutter because you end up basically bonking into it. So because this support here underneath the, I've just kind of mocked this up. And if you are not familiar with section analysis and fusion, this is just a random part that I was messing with cut in half, which is where all the shaded lines are. And then the round part here being the insert of the cutter that I'm going to use. And then underneath it is the tool body. And so basically when you're face turning, because you're turning on the end, you have to have a relief in the cutter. And so, or else you end up with like pretty serious collision. Which is why I think Fusion basically threw up every time I tried to get it to make me a toolpath. I eventually figured out a way to kind of rub the beast in a weird way to get something, but it was never close to what I wanted in the end. Something to do with math, and I was lying to it at all costs around every corner. So I probably just didn't get all my lies correct. Who knows? I'm sure a smarter person can figure this out. This is a quick idea of what I should have bought. This is, you can see here, they make radius versions. Radius versions, you have to call them. They don't even publish their pricing, and we all know what that means. So I just didn't even call them. And so this relief here in the tool is what we're kind of after. And this is a kind of a better view of that. And so this is for grooving in the face of the thing. The relief is cut to a diameter, and then I'm sure there's certain rules that apply here. I even told Fusion that my tool was like 3 microns thick, and there was going to be and it still just was like, no, you don't know what you're doing, which is probably true. So that's the end. Anyway, so what I did instead of spending any money was take a regular lathe tool, and I'm going to stop my share here, and I'll show you let me make this. So I took what used to be a regular lathe tool, and I ground my own relief into it. And so you can see here the kind of grind marks from where I took out. So this all should go straight down here from a profile here. And then the same here, it was rounded all the way straight down, and I've kind of rolled it. It's really hard to pick it up on camera, especially because I Sharpied it and then tried to sand the Sharpie off. And so anyway, so I kind of ground away all this business. Sorry, I can't find my camera. Ground away all that business in order to basically, so I could roll into a piece of material here and have it not grind the tool itself. I want it to grind with the carbide tip instead of here. So there was a few iterations of kind of going back and forth, which is part of the reason I have to do lighter and lighter cuts the deeper I go, because a proper tool would have even better relief and could kind of do a full cut all the way in. I'm not able to do that because I have this hacked together nonsense tool. So since I couldn't get Fusion to work, I badgered it and badgered it and badgered it, never got anywhere with it. So I did eventually figure out that there was a glitch, and if I unchecked and rechecked this one weird setting, then it kind of worked, but it still never gave me close to what I wanted. So I went with the hacky lie to everything method. So I'm going to share my screen again, and I'll show you what, so PathPilot, so everybody probably knows this. I work for Tormach. PathPilot is our control software. I'm doing all this on our machines here. But here's PathPilot. Can you guys see that okay?
Yep.
Okay. So I was able to tell it that I have a tool here. Tool 28 is a radius tool that's coming straight down the Z spindle. And this is approximately the geometry that I wanted. So I played around with these numbers. I learned really quickly that this profiling in conversational is specifically designed for down the side of the tool of the part, not into the face of the part. And I'll show you here, because when I post this thing, and this is just a simulator here, but when I save it, you can see that my roughing tool, so all the horizontal lines are where it's going to clear out material. And then this line around the outside is where it's going to clean up. And as you can see, the roughing toolpath and the finishing toolpath just don't line up. There's going to be bulks of material here that aren't cut. This is going to have too much gouging in it. There's a few spots where it's probably just going to rip a tool through the material. Basically, PathPilot doesn't understand it either. So what I did here was I took this and I saved it and I closed it. And then there's going to be a whole litany of errors here because it just doesn't like any of the geometry for everything that I'm doing. But I can come over here and apply to it. So basically what I figured out is the G71 is a roughing strategy here that created all those horizontal lines. So if I take that and comment it out, then I get a nice, pretty little toolpath that is the geometry that I'm looking for, but doesn't have any material removal, right? So that would just stab the tool in, carve out the shape that I want, probably wreck everything in the process. So as a stopgap for that, I have been manually affecting the length, the Z offset of the tool, and then just rerunning this job 15th out deeper each time. And so the whole point that I'm here at home, I could do all this while I'm sitting there. So I'm going to switch cameras, and I'm just going to walk you through making one of these, and you can see the ridiculousness that I've been getting into, and also hopefully learn a few things. So step one is to cut just the profile of that queen. So that is all pretty straightforward turning. I have a tool in the spindle, or a tool in the tool holder, material in the spindle. I've kind of got everything set up so I don't have to fumble around in front of the camera. And so if you have any questions, just fire away. I'm going to run this real quick. It's just a couple of minute job, but I purposely wanted to run this all at the same time so you can see kind of the whole process. So this is just going to rough out a bunch of material. And unfortunately, I'm running coolant because I want it to run harder and quicker. I could run it a lot softer and get the camera in a lot closer, but then it would take forever. And so this, again, is just a fusion tool path. I'm using a 35-degree insert lathe tool. What else? I think that's about the important bits that you guys need to know.
You had to buy this chunk of brass. How much would it cost?
$200 for each one of those. That's McMaster pricing, which is
and that's
like
for each, that's for each full stick though, right?
That's for each full stick.
Okay. Yeah, not the each piece, each full chunk that you've got.
Yeah, I've got. And so and the fun part about this brass, I'll tell you while we're watching this thing run, is this all is like roughly 100 years old. It came out of a hydro station up on the Wisconsin River, a hydroelectric dam. For a while, my wife was in charge of rebuilding one of the power stations, and these are the hinge pins on the wicket gates. So the wicket gates open and close to affect how much water flows into the turbine and therefore how much power you generate. And so as part of the process of rebuilding, there's 30 hinge pins or so per turbine. And so I got 2 turbines worth piled up in my garage, which is pretty sweet. Which is why if you ever see me, I might have a random top in my pocket to hand away because I just make random nonsense all the time. I've made dozens and dozens and all kinds of brass coins and tops and all kinds of goofy stuff. Ultimately, if I keep her happy, she keeps bringing me material. So that's my plan. So far, I've made in this chess set, I think I did a presentation on the horse or the knight. The pawn is, nobody cares about that. It's pretty weak sauce. I've done the king as well. It's not my favorite because it's, I I followed the original design, so it looks goofy, but it matches kind of the original essence of the project. So we're just about done roughing here, and I'll pause it. And well, I'm not actually gonna pause it. I'm gonna let it run. And so right now it's got a kind of a scuzzed up surface. And so now it's gonna come by and do a real nice slow finish and clean up that surface real nice. So once this is done, then the end of it is still flat because we're only working on that side profile. And so this is where the hackiness ensues. And I'm going to attempt to not make you sick while I jostle the camera around and try to get a good viewing angle for what I'm doing. And this all comes with, you know, a few kind of iterations of testing and figuring out exactly where the numbers are. I have a little notepad that I'm going to follow because I ultimately just have to light everything all the time. So we're going to do one more finish pass. Any questions so far?
You need to scream really loud, I can hear you. Probably.
How long does it take to make an average piece?
This piece is going to be about 4 minutes for this profile, about 5 minutes for the next part, but the next part is just standing here mucking with it. And then the third iteration is just a minute or two, just right at 2 minutes long. So 10, 15 minutes, but that's after I've done months and months worth of work. So however you want to factor that. Like I've got it into this quick. So here is the final part. I'll pop this open and get this rat's nest out of the way. I say final part, that's not accurate. This is the final profile. And I turned it up a little bit at the end just for brevity. So you can, I don't know if you can see it here, but the surface finish got a little not ideal right there. So we're done with that tool. And I'm going to put in that tool I just showed you here again. This is that, oh, nice backlit background. And so I don't know if you noticed, let me crank this up a little bit and give you a little bit different view. And so here, when we were doing all that profile work, this tool came in that way, kind of down across the x-axis. And so now I want to come down the z-axis. And so I'm putting in this tool that way. Again, if I just run this program, it's going to stab that part in, that tool in, and just muck up everything. It'll actually rip the tool out of the tool holder. I did that once accidentally. So what I'm going to do is the lathe right now thinks, the lathe right now thinks we're at 0.9059 inches from the face of the material. If I tell it I've got the right tool in the tool holder. So the lathe thinks we're 1.1106 away from the material face here, which is probably pretty close. So what I'm going to do is start the line all over again. And I'm going to say we are actually 85 thousandths further away than you think. And so that push, I don't know. Oh, you guys didn't see that part. You didn't see the screen. So anyway, so now I've got one single line tool path. Sorry, this camera's a lot closer. You can't see that, can you? There you go. We've got one single line tool path, and I'm going to set this here. And for the first one, I'm going to cheat and keep the enclosure open. See if I can't spray coolant all over myself. So give me a second, and I just have to tell it that the spindle door's closed. Let's put this right there. All right, you guys have to remind me because I forget what these things all the time and then pinch it in the door. So now I've got it set up, and I'm going to hit cycle start and coolant as quickly as I can so that it doesn't spray everywhere. And so there's your kind of cut. So it just took a little bit off that first one. And then I'm going to set my camera back up the way it was. And so now we just do this a dozen times. So I had 85 thou offset. And then we're just going to walk that in 15 thou at a time, and then we'll actually decrease as we go in. So I'll do 3. Let me see if I can get this set up. Does that make sense for you guys?
Yeah, that looks pretty good.
Yeah, so there's going to be coolant spraying everywhere. So we'll see. Let me actually move that a little bit. Okay, so we'll go here. So I'm going to just do, I subtracted 15 thousandths earlier. So now I add 15 thousandths at 3 separate times and run the program. And then it'll scoop out just a little bit more material with each pass. my eventual goal is to, whether I use some good old fashioned Excel or Python hacking and create a G-code program, or push it even further and learn macros, or even just a for loop. I want to make this a little bit more automated, so I don't have to sit here, because I'm actually typing in the Z-axis DRO every time. But we all know how that goes. Like, improvements pretty much never happen. This way works. I can make a few parts that I need. I'll probably just continue on with another part. And so now that would be, sorry, somebody asking something?
Yeah, so I get what you're doing with manually adding the Z side to work it in. Why is that something you can't program? Just to say, hey, make this cut 10 times. Is that what you're saying? You have
It's hard in G-code to provide an offset. Although you could just, yeah, you could do like a G54 0 each time and shift it.
Well, yeah, I mean, if you were making a bunch of description, just write that piece of code, and then I guess you're.
Davey, I think Sean's volunteering to write code for you.
Well, I can't hear everything you're saying, and I bungled up my program while we were talking, so give me a second while I recover. Here, I'll give you a clue of what I did, because I do this. This is the hard part about like working and presenting and talking on the video and all that all at the same time. So what I did here was I've been editing into this Z-axis DRO right here, and notice it says 0. It's not supposed to say 0 right now. I actually typed in the value, so I've been adding 15 thou at a time like this. And then instead of hitting enter, I hit Z0, because I was like thinking about what Sean was trying to say and all that. So if you give me a second, I can recover and or crash my machine in front of you. So I'm just going to figure out what this value was. Let's do this. Let's do 0.98.
Monthly hackerspace meeting.
Okay, let's try this. Nope, that didn't work. Let's do plus 8.9842. 15,000. So that's not the one. Oh, this is the one I want.
So the status window that he's reading, each time you zero the Z, it tells you what value you were at. So if you accidentally hit a button, it at least records where you were. It didn't used to do this. This was a feature add a couple of years ago, because it used to, if you hit 0, you were just totally screwed. It wouldn't tell you anything. So at least now it records what it was when you zeroed it and when you changed it.
So I should be at 0.9511, and I don't know if that's before or after I set my last tool off, or kind of cutting increment. So you guys get front row seats. I'm going to slow it down when I run it this time, just in case. I think right now we're going to be cutting a 15 thou pass. So anyway, so Sean, I think to answer your question, hold on, actually. Oh, look at that, like butter. To answer your question, Sean, yes, if I knew what I was doing with Fusion, or if I wasn't trying to hack everything together, this should be a lot easier. I could buy the proper tool and probably make my life a lot easier. But what I think I'm going to do is create a for loop that counts the iterations down and then decrements the Z-axis, or actually it would be adding to the Z every time. But that involves learning how to change the work offset from the G-code program, or changing my values in my G-code, like the coordinate values for every line. And that's just something that's going to take a little bit of time to figure out. So this was the third and or fourth pass at 15,000. So I was supposed to do 3. I got sidetracked by answering questions and getting all miscombobulated with my work offsets. But anyway, now I'm just going to go to 8 thou depth of cut, just to get, because that tool is just burying deeper and deeper into that material. And the beauty of this is I can tell when I'm done when the little nipple in the front loses its flat. And so I should do 3 of these, and then we'll move over to the fourth axis portion of this, because there's a mill component too. For anybody that noticed, there's the crown has ridges. What, I don't know what you would call that. Huh?
Castellations.
Castellations?
Yep.
Oh, neat. Didn't know that word. See, there you go. You all learned something. So I'm going to call it done at that. Normally I would do a couple of cleanup passes, but you know, for the sake of this here presentation, I'll show you what we have here. And so, and I don't know if you caught this, but I purposely made this tool path come flare out, and then this one, when I was cutting the profile, it flared in, and I did that so that when they met, it would make sense, you know, because I didn't want to kind of create this finite point that I had to adhere to. This way I can kind of keep rocking and rolling until I get to the point that I'm looking at, you know, until I get to a point where this is nice and round and everything. So from here, I'll save you the work of watching me do it. But let's say I have this, through the magic of time, I have it set up in the fourth axis now. Because now we need to cut the castellations into here. And I can't really zoom this in any further. And I did clean my window, so you have a reasonably clean view from the coolant. And so now here, what I did, so this is also an exercise in setting up work offsets. So I've centered the X or the Y and Z to the center line of this material here. And then I've centered my 0 for X is at the tip of the nipple here in the crown. And I just did that all with a probe kind of off camera before I showed up here. But now we're just going to take an 1/8 inch ball end mill and cut those the grooves in there to make that castellation. And I might cheat and open up this cabinet depending on how much coolant spray I'm getting here.
How toxic is that coolant?
How toxic? The MSD, the SDS or whatever, the data material safety data sheet says that it's non-toxic. Whatever that means.
That is a good answer.
And so I don't know if you saw that, but the axis rotated. So I've got, these are 60 degrees apart and there's 5 of them. And I did this in Fusion using rotating a 2D tool path. And so I created that horizontal line that we're following. I'll show you, I'll pan over here real quick and show you kind of the tool path here is that kind of horizontal line there. Or not horizontal, it's a 40-degree angle or something like that. And so I created that on an offset plane in Fusion and then told it to trace that tool. And then once I got a tool path at so-and-so depth of cut, then I just said, okay, now rotate it around the A axis and do it 5 times. And so from here, once this part gets done, cutting these grooves, then I just throw it back in the lathe and do a simple part off technique, or not technique, but a parting operation. So that pretty much concludes my presentation here. Does anybody have any questions that haven't been asked yet?
Yeah.
Yes, do you have a vertical chuck? Did you try doing these vertically with the radial cuts, or?
You mean, so I believe the question was to put it in the mill this way and do this, or this, you mean? Yeah,
cut the 6 slots vertically.
Yes, yeah, I could. That would make sense. I honestly never even thought about that. There's a bunch of stuff that I didn't think about and didn't do, partly because I'm friends with you guys. I don't like doing things the easy way. And so some of this has been an exercise in like pushing the limits and trying to learn as much as I possibly can. So like another way I could have solved this problem was with that ball end mill. I could have just come in here with on the mill and done the same thing. And you guys are coincidentally seeing my machine with that 3-jaw chuck on the table. I put that on last night to work on a different project, and I forgot it existed for a while. Anyway, so yes, I could have.
Any other questions, anybody? All right. Davey, your job is to sell these things. So if we want to make our own chess pieces at home, how much money are we out to buy?
No big deal. I'll get you into one of these 8Ls for like $12,000, 770M. We'll call it an even 30. No big deal.
And do you throw in any brass with it?
We get one stick of brass with that, or how's that work out?
Is that Sean asking? I think Sean already has a couple of sticks of brass.
Brass.
I'll tell you what, we're free shipping. That's the promotion right now. Anyway, I'm going to log off here and I'm going to come see you guys. So I'll be there as fast as I can.
Thank you, Davey. We'll see you in a bit.
Yep.
All right, EJ, you up?
Sure.
Don't sound so excited. We'll see. Well, EJ's getting set up. One of my former high school students brought these over for me. These are really cool. They're 3D printed puzzles, but they're really small. So they're like little punch out. You knock out the parts, and you can build whatever it is. So she's got a train, a horse scene, balloon, a mountain, rocket ship, and a fishing boat. But they're really neat. It's a clever way to make a puzzle. That's kind of cool. Do you want to share your screen from there? Yeah. Here.
Oh, should I zoom in?
Yeah, you should just zoom in. That's definitely the easiest thing, so it doesn't mess up the video. That's all right. We'll let it slide this time. Yep. So EJ is going to talk about making timer. Yeah, just say join. I can view as fast as I can. Fine, you're good. You don't need audio at all, so it'll work. Then you can just share screen. Oh yeah. Where's the fun on that? Yeah, that's fine. But so EJ is going to talk about in making a medicine reminder in about 4 days, I think. So he has not built hardware things, I think, in the past. So this will be entertaining.
You're not kidding.
Yep. So you're here, so you can see what you're sharing.
Yeah.
I'm not sure what you. Yep. So that looks the same now.
Okay.
All right. Cool. Yeah. Like I said, you can see what's up here.
Yep.
I'm gonna turn this a little bit.
All right.
Take it away, sir.
All right. Just moving some things around so I can see what's going on. All right. Hi, everybody. I'm EJ, and I have had a need for a while and have looked for various solutions and didn't find one. So as Chris said last week, I decided to just bite the bullet and try and solve the problem myself. So I just realized I left the actual fill containers. I'm going to be talking about this here. So we're going to get that. So I have to take pills twice a day, and so I have these two pill boxes. One of them has Monday morning, evening, and then Tuesday morning, evening, and Wednesday morning, and Thursday. So seven little chunks of this 7 different slices. And then I have a second box that starts on Thursday night and goes Friday, Saturday, and Sunday. And I go back to the first box. And they work great. They're like $2 at Walgreens or $3 at Walgreens. But they don't have any sort of reminder. So I've been using a reminder on my phone, but often that phone is in like another room where I'm not, and it's ringing and buzzing at people who don't need to take my pills, and it's not buzzing at me, and I do need to take them. Or I'm on a call and I snooze the reminder, and maybe I hit the wrong button and it actually cancels it, and it doesn't remind me. So the idea that I had was to create little 3D printed inserts in each wedge, and use up to 3 magnets to binarily indicate which of the different wedges is currently selected. And then one of the boxes will have a magnet over here to distinguish between the two. And then I'm currently 3D printing a box that will go around this. Anybody who's looking online, which is basically an Arduino, and then a bunch of jumper cables over to some LEDs and some switches. So I can turn on the LEDs with these switches, assuming they are not falling out. And so these LEDs and the switches associated with them basically correspond to the magnets. I need Hall effect sensors to actually read which magnets are in there and which are not, which ones are in there, so I can determine what day of the week is currently selected. As a placeholder, I'm just using buttons in place of the way that the magnets would be sensed once I have those sensors. The rest of the logic is, I'll just quickly take you through a README that describes the project. So,
How did you write all this code so fast?
well, that's kind of a whole other presentation, actually. I should probably. It's a presentation I've given a variety of different times. This README will give you some sense of the answer to that, which does involve ChatGPT. I know that's the thing that you were pushing at. I can't fault you for that. I've been here before.
I've never seen like this many comments in your code in life. That's
That's how you know.
That's how I know.
Yeah, again, that's a whole other presentation we could do. Comments and code. So at any rate, this describes the basic project. It describes there's two boxes and how they're going to be used, the two pillboxes. Describes the two wheels and how they're intended to be used, the different slices, the day-evening configuration, and so on. It describes how the binary logic is going to be used to identify. It has to both identify which pill wheel is currently installed, as well as which slice is currently selected. And so this describes how I'm going to use the Arduino, which pins are going to be used for which parts of the sensors, which are going to be used to sense the buttons, and which ones are going to be used for the LEDs and the speaker, and so on. It then describes, at the moment I have time sped up, so the demo I'll do when I actually start pushing the buttons and so on, and explain what the lights mean. I have time sped up where each minute is actually only 4 seconds long, and there's only 4 minutes in each day. So we'll be able to get through a full daily cycle a couple times in a minute. So this describes that and how time works basically. And then how reminders work. So how long each reminder is going to come on and stay on, and what that sequence is going to look like. And then this is a flow chart of the basic logic that drives, you mentioned I did it in 3 days. It's based on this state machine, which is one of the things that simplifies implementing something like this. So I'll just quickly step it out here. It may be hard to see, but basically it starts in a state of idle where it's just waiting. And then if it detects movement, meaning that the wheel turned, it basically goes to a debouncing phase, because you might have just bumped the button and it started to move, so the sensors changed, it goes right back to the way it was. So it goes to a debouncing state, and then if the index goes back to the index that it's just on, it goes back to idle. If that debounce finishes and it then should actually handle that movement, one of the ways that I thought about providing input to it about what time it is or when the bill should be set was that I would go 1, 2, 3, 4, 5, 6, 7, 8, 9. So the initial design allows you to count how many times the button was pushed. As it is, I've simplified that, and I'll explain that in a moment, but it does currently support counting how many times you push the button. So it always counts it, then it waits for more movement. If it detects another movement, it goes back to debouncing. If it debounces, it counts that movement, comes back here, and then once you stop moving, then it goes to movement detected, which is when it would potentially, before taking your pills, stop the beeping and move on to the next time, waiting for the next pills. Before I go any further, I've said, if there are any questions that I can answer.
You really have a problem remembering to take your pills.
I do, yeah, and it's really important that I take them. So So this is a picture of the state machine that drives it. This is an English description of each of those states and how they work and what they should go to and from and why and so on. For each of the different states. And then the different sensors, the different pieces of hardware, how many of them I need, how they get used, etc. So this is just basically a README describing, it's like a specification for the project. And then the code basically is based on this same thing. So the code just runs that little state machine, detects what's going on. Originally, I had thought I would have some sort of screen to communicate what was going on and have some sort of buttons or something to be able to set when the pills are taken. And then I realized it's actually much easier to not have any input or output. And instead, I just plug it in when I take the pills the first time. And then it just counts how long it is until I take my pills the next time. And then it uses those as the times that the pills should go off. And so 24 hours later from when I took those first pills, the way it works is it will beep once. So if I'm not in the room, it will just go beep and stop. And then a few minutes later, if I still haven't taken them, it'll go beep, beep, and then stop. And so it can just kind of gradually increase in urgency until it's going beep, 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 and then I actually need to be taking them. But then I take the pills and I push the button and it swivels to the next spot and stops beeping. And that's basically how it works. Questions? Yeah.
So if, let's say you got it off 10 minutes, taking your first pill.
Yep.
Instead of like 12 hours and bucks.
Yep.
Would that start compounding? I mean, would that be starting? Nope. It's because it's resetting every time you move forward.
The reminder is completely decoupled from the two times. When you first turn it on, you take your pills. That's the first time. Let's say it's 10 a.m. It doesn't know it's 10 a.m. because it's an Arduino. It doesn't have a clock or any way of knowing what time it is. So it just goes, oh, okay, this is 0 for it. And then it counts. And if you then take it, let's say at 9 p.m., 11 hours later, it's going to record the second alarm is 11 hours into the day. And that's it. From that day forward, when it gets back to 0, it'll alarm. And then when it gets to 11, it'll alarm again. And so on forever. The alarm then can be snoozed or get more aggressive, or is just its behavior is decoupled from the reminders, which need to happen at specific times of the day.
So you're setting the clock by the arbitrary moment you first.
That's right.
Use it. But why? I guess I'm curious why you do that instead of setting the real-time clock.
100% for simplicity. Because it's easy to do. I plug it in. I take my pills. I wait till my next pills. I take them by just taking them and clicking the button, and then it can remind me of nothing.
But let's say you were 2 hours off, make it to the question. So instead of 9 o'clock, you put something happened, you have to take it at 11.
Huh?
Some pills you don't necessarily want to, still want to take it at that time.
Yes.
You don't want to.
So those are features I could potentially add, like an actual snooze, like please remind me again, but I would hit a button. And the main thing that this offers that I didn't have with any kind of phone-based reminder is it knows when I'm actually taking this. And none of my other devices or situations or solutions knew when I'd actually taken this. And this can actually, so it's beeping right now because I haven't taken my pills and I should be taking them twice a day. So right now it's daytime. That's what this means here. I made a little camera as well. So there's 4 lights. The bottom light is the wheel sensor, like is it on wheel 1 or wheel 2? And then the third light is the day-night sensor. So right now it's daytime. If I push this button now, it's nighttime. Now it's daytime. Yeah.
So does that connect to the pillbox remotely, or does it?
No, so this is going to be in a little box that I'm currently 3D printing.
Oh,
It just
okay,
didn't finish
okay.
quite in time. And then this will just sit on top.
Okay.
And the Hall effect sensors will
All right.
measure the magnets. And when I'm done, I'll click the button and it'll move to the next one. And then this will know that I've taken the pills and will stop screaming
Okay.
at me.
I thought they were separate.
I'll pass this around. You can see the magnets.
Block, and you're trying to find the pillbox.
No, they're going to be attached to, they'll be attached to each other. They will be together. And then, so right now it's basically every other minute. Once it starts going off, I then have to go to the next spot. So at the moment it's daytime on day 1. So when I flip it, the next sensor will have it be nighttime. That clears the reminder. 4 or 5 seconds later, or 8 seconds later, when we get to the next reminder, it starts beeping again. And so now I need to take my pills. So I click the button in the middle of the pillbox and it goes to day 1 AM. And so now the day 1 light and AM is clicked. And again, now the reminder starts going off, so I can make it day 1 PM, not day. And thus it continues, and each day it can then go to day 3, and then day 4, and then on day 5, I'd be switching to the new pillbox. And it would then be night on day 5 and 6, 7. Yeah, so that's basically how it works. If I put the actual speaker in, which is what I would have, then it will actually tell me, and then make it nighttime. Does 1 beep to indicate it's done. That's now the next day, so I'll go to the next day, beep, and now it's done. Now it'll stay off. 8 seconds.
David, your question?
Yeah, can I attempt to interpret Sean's question? And
Yeah.
If I understand what he was trying to get at and how this works is, your first iteration, that when you first plug it in, that you have to be on. You have to pay attention to your own personal clock and make sure that at noon you take your bill.
You have so
Or noon
here's
is
how it
right.
actually works. When you turn it on, it doesn't work.
Right.
And it assumes that you are on, let's say it's the morning of the first day. So or let's say it's not. Let's say it's the morning of the third day. So you turn it on, it doesn't do anything. The morning of the third day, you take those pills and you hit the button, it now knows, oh, it takes its morning pills after that.
Yeah.
It records what time of its own day. It's more aligned with our day.
Yeah.
But it just knows 6 hours after I start, it one takes the morning pills. Or the first pill. I might turn it on in the evening, the first pill to actually. But basically it knows that timing, and then the next time you take your pills, it's like that. For the second time. And it knows what you can.
And that's what I was saying, yeah, so those first 2 times, you have to manage your own time. And
Yes, I see what you said, yes, it doesn't remind you the first 2 times. One of the things I've thought about doing is having it beat by default 12 hours later.
Yeah.
But it's, at the moment, I'm just being.
As long as the battery is. As long as it's
It'll have a flexible. And theoretically, again, something that could be added is like a backup. Get some plug and actually stuff. With battery life. But this is just. 0.12 here. Something like that, yeah.
Well, I think it's a fascinating idea for like, people to, remember it. Because a lot of times. Sometimes you look at it and you go, I still know, can I take that from this morning, or did I forget to fill up?
That is the entire purpose of this. That can't happen by construction.
Well, no, I mean, I think we have to also take a step further, like we lock the folders. So you couldn't accidentally turn it to Tuesday, take it to Tuesday.
Yeah, let me.
The way it works, it clicks through. So, and then the thing is seeing the magnet, you should pass it around.
Yeah, I'll pass, there are 2 of them, I'll pass them both around.
So to be clear, the reader is reading the fill folder state, and so it's actually got
It
magnets.
knows, at any point in time, the Arduino knows the specific day and time and what wheel you're currently on. So let's say you click it twice by mistake, and you're now just totally on the wrong day. It'll start beeping because it's not correct until you get it back to where it should be, and then it's stops. So it has, because of there's actually 4 magnets, and with 4 bits, you get 16 possible combinations. There are actually 14 slices of pie, so.
So that fill holder sits in a box that contains the Arduino and the sensors, and it all will be plugged in. Whoop, baby.
There'll be a box like this, and the box, that whole container will just sit on top, lining up the sensors. Jim had an excellent idea today for how to do that. I've been going round and round, because originally I pictured it to be kind of prongs that hold it in place, but I really want to be able to just pop it off to take the pills, because this is a really convenient. That's really convenient. You open up the door, you pour out the pills. Having a big Arduino connected, having a big box attached that's connected to the wall of this facility. So then I thought just positioning things, but then the orientation becomes tricky. But we're using magnets, so we should be able to just put a triangle of magnets and then just pop right on and orient itself so that it's all line
Couldn't it be a
correctly.
third off every time?
No, because it'll not be, if it were an equilateral triangle, yes.
Gotcha.
It'll be a obtuse
Okay.
triangle. It won't fit one way.
So you'll attach magnets to this, is what you're saying?
Yeah, so I'm picturing just publishing it to an open source repo that will have the code and the STL files for the inserts. Those pillboxes, you can get them basically anywhere. They're like $4 or $5, depending on where you get them. And then a list of the parts. And for the inserts for that, I just used a drill. So I just went, and it worked pretty well. I stuck the magnet in, it stuck pretty easily. The actual little wedges, I was trying to figure out how to get them in, and Chris was going to mix up some epoxy for me, which would have been kind of a lot. And he was like, well, figure out where the magnets should go in the little wedges. And as I started to do that, they kept popping out and grabbing onto themselves. And then at some point, one of them went underneath, and the other one was on top, and they sort of wedged, and they were not moving. And so at the moment, as that comes around, that's how they're all staying in place, is all the places where there's a magnet. There's just another one on the other side, a little hot glue, modifies the box. I don't have to deal with the mechanism of the moving. And yeah, seems to work once I can get my hand on some ball effect sensors. And get the box to print. Apparently it's going to take 5 hours the way I first had it designed, so.
How do I index this? I'm stuck on T.
Yeah, I broke both of my existing. They're not turned anymore. I'm good at it, especially with these little inserts, which don't really fit. They're prototype versions that sort of squeeze the box and make it so it won't turn. But even so, it does. They just.
I think you're supposed to look Davie straight in the eye and say it doesn't. All right.
It worked when I gave it to you.
Any other questions?
Thank you.
All right. Yeah. Thanks.
Scott is our last presenter.
All right. So.
AJ, you want to drop your signature?
Yes.
Better sample drive.
How long have you been working on that?
I want to.
What? 3 days.
3 days?
Yeah, so on Friday.
Jesus.
Hey, ChatGPT did all the work. All right, let's be clear here.
I would should have decided. Well, I understand it's a little like college too. Should that be? Yes.
Yeah. All right, so my name is Scott. I'm a member here. I'm going to talk tonight about a project that Chris and Dave Franchino and I have been working on to implement a fiber laser cutting machine. So, you know what's great? One of the great things about this place is that we make tools accessible to people. If you've used a 3D printer or the CO2 laser that we've used, you know, you can do some digital design. You can be holding a real part in your hand. That's super cool. But the CO2 laser has some constraints. It'll cut wood, it'll cut acrylic, great, but it's not going to really touch metal at all. Oh, thanks. And so we have the machine shop, of course, and the welding shop, and the plasma CNC to do that stuff. But we're kind of in the middle of this rapid evolution right now of the availability and price of fiber laser cutting machines. They're really becoming more accessible and cheaper all the time. And they have the ability to cut metal with the laser. And anytime you can cut metal with a laser, that's cool, I mean. So Sector67 inherited, I think, from Tormach. I don't know if this is around from this. Yeah. From Tormach, we inherited a system that they got in to do some prototype testing with, and it eventually came back to us. We inherited a 500-watt fiber laser system, which is a relatively, as far as fiber lasers go, low power. But it looks like this. It's back there. But it is capable of cutting up to probably and slightly over 3/16" mild steel, slightly less thick aluminum and stainless steel. And we basically got the laser source and sort of the basic components of what could be used to build a fiber laser cutting system. So So we did the work to turn it into an actual machine that works. There's a lot of physical kind of machine work to make that happen. So, you know, the motors move this laser around on top of a piece of metal to do the cutting, to cut out parts. So there was a lot of machine work. There's a lot of software and electronic work to integrate it. I'd say it was about 6 months of volunteer work on and off. Roughly speaking, I didn't really track very closely. There was a lot of apartment work that sort of fell in the middle of that took up time as well, where we weren't moving forward on the laser. And this is the kind of laser that will blind you instantly. So, you know, the CO2 you can watch through the window, cut out your pieces, and it's all well and good. This thing needs to be, despite YouTube videos you might see online of people standing by these things watching, these are the kind of things where they do the rust removal lasers, and they just like point at the thing. Despite all that, it is not at all safe. This will blind you, it needs to be fully enclosed, and so there was work.
So you have no idea what it's doing when it's closed.
Well, we implemented cameras so that we can see it when it's going. I have a video later. So there's a basic gantry that we got working. Dave did some work tuning that and aligning and getting it to move. There's a laser head that's a floating laser, which means you can Z down into something. So there's X and Y and Z dimensions. You can Z down, it'll hit the material, and then it'll keep going down, but it'll hit a sensor that says, oh, reach the bottom. So you can use the head to sense material if you want to do that. We implemented a Hall effect float and home switches so that we could accurately home the machine so it knew where it was on the table. And a lot of time, the control system, the laser head that this machine that sort of came with sort of our set of components to assemble this was a standalone height control head, and it never really worked properly. So what we did is we implemented a Z motor control and closed loop control for Z head height, which I'll talk a little bit more later. We made a full plywood enclosure, and basically Dave did some work machining a new laser head with coolant channels. So this is what the machine looks like. You can see this is the laser where the laser comes out right here. There's cooling channels in here that help to keep the optics of the laser cool when there's 500 watts of laser power flowing through. This is the gantry I was talking about. So this is a screw here. So this head moves back and forth this way. There's a screw here and this screw here, so it can move back and forth that way. And there's a screw here in the Z, so the machine can move up and down. And here's our nice stack lights. So it warns you when the laser could potentially be firing, so you don't have, so there's extra little bit of safety there. Despite the looks of the whole thing, safety was a paramount concern in the build and the doing of this project. Yeah, so there were a lot of physical parts of the machine that needed to be fixed. We need to implement a control system for this. So one of the issues with laser cutting, this is the case on the CO2 laser, it's also the case much more so for the fiber laser. You need to have the focal point of the laser be in the material that you're cutting in order for the power to be concentrated enough to actually cut. So the machine has a laser head that I showed earlier. In this laser head is a lens so the power transmits relatively unfocused, but then when it gets to the point of cutting, it focuses. And that's where you get, when you get 500 watts into an infinitesimal point, it makes enough heat to cut through metal. That works great if that point is right on your metal or right in where you need to be cutting, but if it's slightly off, you're gonna not be able to cut through metal. So the height of the laser above the material matters a lot for these cutting systems. And yeah, Sean, question.
So one of the first things you said was that aluminum stands kind of smaller than steel.
Yeah, less thickness. A part of what enables us to cut mild steel is carbonated steel, and aluminum doesn't have that. The stainless, I think it also doesn't oxidize. Yeah. So there's in addition to the laser, there's a high gas flow as well.
Well, I was curious about that, but I guess the second question is, the 267 cut. Can you increase that down to you run a second pass? Always if they're too small, let's get that okay. You know what I'm saying, and move that focus link down.
Yeah, I mean, there's plenty of experimentation we're gonna need to do to see if this thing works, but normally you don't see them. I mean, you'll see them do like a chamfer on a hole or something, not a gouging operation with a laser, which is what you talk about, like gouge halfway through and finish at that. I haven't seen it done really. You know, you could run slower potentially, or you could go up and down. I don't know, but I don't see that done.
Well, it's really not, in theory, as long as I'm able to see, but it made it feel like, but, and it wasn't getting away from focus.
Yeah,
The second pass. But if you're.
Turns out it all splashes up. It's problematic. It's kind of run a plasma place. What also happens is once it's oxidized, it forms like a crust. The crust no longer channels and flows. So they do use what you're talking about to cut really thick metal. So because you're limited on the focal plane of the laser, you can't make a magic laser that has a deeper depth of focus with the same kind of concentration. So they run a piezo element in the lens and actually walk the lens up and down in real time while it's moving, watching a camera for feedback. We don't have a head like that, but that's what they do on big lasers. That we fix. Yeah. So yeah, that head was like twice the price. So.
and this, to be fair, this is really a test bed system. It's a relatively small table. It's a relatively low power fiber laser, but it allowed us to prove out the aspects of doing the control system for a fiber laser, which is quite a bit of nuance to do that properly. And one of the big pieces of the nuance is this height control that I was talking about. And so metal, you might think it's flat. It's not necessarily flat. And when you're putting heat into it, it's especially not flat. It will warp as you're cutting. And the tolerances on, you know, what you needed are in the hundredths of an inch kind of tolerance. And so what they do they sense the height and they adjust dynamically the torque, what they call the torch height, to be able to maintain the height. And the sensing system for these fiber lasers is typically a capacitive sense system. So it's using a very sensitive capacitance sensing system to know when you're close to the metal and exactly how far away you are. And I'll show a video that kind of demonstrates that. But one of the big mysteries of this that we had to solve to enable this to work properly was this capacitive sensor, which normally it's like, oh, here's this device we found. It's a capacitive sensor. There's some data sheet somewhere on the internet. We go find it and like, life's good. We hook it up with the right voltages and we get this stuff out. I am telling you that no data sheet exists for this component on the internet that we can find. We mined everywhere, all over the place. Ask questions on various YouTube channels, or talk to resellers, offered to like pay people money to go to their machines and sense, read the voltages. Nothing. We were not able to do that. So I got COVID. And I had some time on my hands. You can see there's like, these things are potted in like more than a half an inch of epoxy because they're meant for like very, water type environments and all of that. And so I depotted the thing painstakingly.
Yeah, a lot of time.
Yeah. Well, so there's all these like, oh, you put it in boiling water and it just peels off.
Epoxy though?
Yeah, no, I had to take a soldering iron with a hot tip. Scrape away
Oh,
bits at a time.
Hopefully with COVID, you can't tell.
So this was half of the board and there's another half. This was an image I took from like so then it was like I destroyed some of the components. Most everything was readable, but I spent a little time on the Reddit, like helping me identify this electronic component board. I got some good help there. We eventually actually did figure out what this capacitive, how to interface with a capacitive sensor. It turns out it generates about a 3 megahertz variable frequency signal depending on the capacitance range that you're in, which 3 megahertz signals a pretty fast signal for PCs to sense. But we figured out how to interface it cleanly with our PC-based control system. We used for the control board I/O in general, we use what's called the Lathes 7992 Ethernet board, which has it's basically interfaces to a PC via Ethernet, and it has onboard field programmable gate arrays to do programming, so it can do fast encoder counting, super fast color counting, drives stepper motors really reliably. Not, the PC is not necessarily a real-time device anymore, but this card allows us to do all the I/O to drive the machine in a very reliable way. And we had to kind of go into a special configuration mode in order to count to 3, get the 3 megahertz signal, but we were able to do it. Integrate that reliably, and just gonna pull up this video and run it. This is last night. Chris and I did the very first test cuts on the system. So these are the most boring possible pieces we could actually to do. But this is a video here.
So,
Whoops, what happened?
you can see that the power cable is now in.
The computer explodes.
Yeah, that was
I wanna watch that video.
tomorrow. Okay, so this is a video of the machine. Here's the camera. You can see the laser head going down to probe, and then it fires, which you can see the overhead view here. It's moving in the square. You can kind of see it cutting on the square, and then it eventually gets around, and you can see this is a LinuxCNC interface for plasma cutting typically, but there are a lot of analogies between plasma cutting and fiber laser metal cutting, and you can see it got through the part there. But there's something I want you to show. Why is it on autoplay? Are you kidding me?
Oh man, who built that thing?
Okay, well this is a laser cut gingerbread project I did a few years ago. That was kind of fun. Why is it doing this? All right. It's on, autoplay is off. My God, who has autoplay on these days? Okay, so I just want you to watch. So
This is your first time using YouTube, Scott?
this is the
You middle clicks.
okay. What the hell?
You can use the arrow keys. Definitely the easiest thing in that thing.
Okay. Yeah, I don't. Okay. It's not gonna autoplay. I'm sorry. I am a computer professional. Okay. So I'm gonna pause this video, and I'm just gonna orient you some on the machine. So this shows the Z position. This shows the laser head camera. This shows as you traverse around. So as this goes here, you can watch this Z position. It goes down. It doesn't actually use the float head. We use the capacitive sense. When it actually touches, it changes radically. So we're able to make what they call an ohmic probe of the system. So I'm going to just move forward like frame at a time here. And you can see this Z value is going down. It's getting closer, closer. And you can see this where it's the 66, 64 up here. Right up here, that's the sort of scale capacitance value of the system. And so the capacitance, you can see it starts to go down as it gets closer, changes quite, and then when it's touching, the camera slightly lags. The Z is redefined as 0. Our program touch height here was 0.06 inches, and there it starts to fire. And now as it goes around, I'm just gonna play this again. Watch the Z. The Z actually changes quite dramatically because this is a thin piece of material, is poorly supported, so it was droopy. The Z actually goes up a little bit, and then it's down to 6, 5, 4, 3, 2, 1. Almost goes negative, then it goes back up to the same corner where it started, and then it gets basically back up to the place.
So is that the actual head adjusting through the metal?
Yeah, the head is literally diving and raising as it senses the capacitive distance from the piece of metal. So
it's adjusting as the metal is
yeah,
moving.
the metal wasn't moving probably in this case. The metal was just sort of like not flat.
Oh.
But if you put a lot of heat into it, it certainly will move as you go. So, so that's.
If you're cutting something in the piece you're cutting out is super thin, is there potential for like one side of the cut to rise up before the other?
Yeah, there definitely is. There's something in here called void anti-dive. So there's another thing too, where you cut out a circle and something drops, for instance, and you're going along it, or you go back over a cut that you made, you might sense and it might dive into that hole. So there's some software features that are really nice. Because we're doing the Z height control, not on a standalone thing that's just on the machine, but because we're bringing it closed loop all the way back into LinuxCNC, we can do things like do the void anti-driver mesh mode. On here, you'll see this. It's if you're cutting expanded mesh or something like that, where you just you know it's gonna go like this otherwise in the mesh, but you just tell it that, and it basically then maintains a smoother cut. So there are some features. If one side goes up, yeah, that's going to be a problem. Or if you cut a piece even and it halfway's tilting on one of the things, that definitely the capacitive sense you could have trouble. If it touches, it'll actually stop. Yeah.
How big's the table area we've got this?
This one right now, it's like 2 feet by 2 feet, probably something like that. It's not a huge table. But what we're talking about is using the plasma bed eventually in the welding shop. That would be a much larger. Yeah, TJ.
You're in LinuxCNC. Could you theoretically use a camera and have the camera to see how high you are and know that it's mesh and basically just like be better?
There, you know,
Next project,
if you watch this, what happens to this camera when it fires the laser? That might answer your question. There's a ton of optical interference, with a laser cut in particular. So
not a camera, some sort of like.
Yeah, there's been a lot of effort over the years at trying to figure out how to do this. And with plasmas, you use voltage, and with lasers, you use capacitance. Same with flame cutting, you use capacitance. It works really well as the thing, so it just doesn't. There's really no.
Unless you're trying to cut that.
Yeah.
I was gonna do that.
yeah, the capacitive, it's going to need to be metallic. And this fiber laser, I actually don't know what else it would cut out.
Nothing. Only cuts metal.
Yeah. So this is other questions.
Yeah, how up and down is the Z up? Because I know mostly Chris is doing this, doing clean shovels.
Yeah. We have not literally the 2 pieces you got to pass around there are the 2 pieces we've done. It seemed to,
so could it do like a cup or something? I mean, so what is the?
No,
We can put a fourth axis on it. It'll do anything.
yeah, I mean, you could cut the sensing part. The head itself is, it has to be relatively flat.
Okay, so
for that to
flat.
Yeah, like if you see I don't know if I capture it very well here. You can't really see it, but there's like that much of a chamfer on the head, so that it can't dive into like a really low.
Where is the capacitive sensor in this? With that ring around?
Yeah, so there's a copper part here that's an integral part of the laser. It's shielding the laser. There's a copper nozzle basically. That's electrically isolated from the body of the thing with a ceramic ring. And there's a coaxial cable that comes off of that goes to the capacitive sensor. So it's this, it's a box like this on the side of the head with the littler red side is a coax going to that copper ring through the machine, through an electrically isolated path. And then the 4-pin here is going a long ways in a shielded way to the control box.
So I pass around those coins too, so it can also do the like engraving.
I was cheating. I used the other fiber laser.
Oh, there you.
The type of laser is correct. This laser is continuous wave, so it's meant for cutting.
Yeah,
But you can engrave with it. You just turn the power down.
Okay.
But it would be really inefficient compared to the other
But those are
lasers.
really smooth for.
Yeah.
Yeah, and those like that 50. It's a 50-watt
It's a pulse laser.
pulse laser. That's a super cool machine as well. And as a part of that, like these things are becoming cheaper and more widely accessible.
The story that Chris likes to tell is that you built the first CNC mill here, basically with hope and duct tape. And the very first part that you made was a gear that was for an injection mold. So I just have to say, for all of us, we're a little disappointed that we get a square as a first.
Okay, there's gonna be a lot. it's gonna be a lot cooler parts coming out of this trip, believe me. So it was getting kind of late last night, and we just needed a part that we knew, that we could cut out. So there's a conversational mode in this user interface, the QT Plasma C, what they call it, or some people call it QT Plasmac, that lets you do bold hole patterns and squares and polygons.
Can't all make chess pieces.
Yeah, exactly. Yeah.
But I think, but ultimately, I think the question before that was the answer to that. You can't, I mean, you're just cutting 2D, that's all you get.
It is a 2D process. I mean, you'll see some people chamfer holes and stuff, but like it's fundamentally it's a 2D process. It's really, analogous to that CO2 laser, but for that.
You say they're chamfering holes like with a tilt on the.
No, they just use the power on the edge of the hole and make a chamfer. I mean, it's sort of faking it, but yeah.
They do put these type of lasers on the end of robot arms, and then they'll do multi-axis cutting and stuff with it. Yeah. Great. But yeah, they do all sorts of great stuff.
Maybe this is what was just being asked and discussed. If you had a big block of steel or aluminum or something, could you theoretically like change the depth?
You can chip at it, but you have what you need is a 3D scanner that you ablate it, and then you scan it, and then you figure out what to do next, and you do it. And that industry wide, I haven't seen that yet. So that's where it's heading, because what they'll do is they'll take powder, and you spray powder at the surface, and use the laser to melt it on, and you build a 3D print it.
And the pulse laser in the machine shop. It's basically layer by layer ablating of whatever material. I don't know if some of that got passed around or something.
Yeah.
But yeah, in theory, that's just time to go deeper, really.
Right. Yeah. Yep. Cool.
Yeah. Okay. Any other questions?
Can we watch that computer explode?
Uh,
Scott, was there a lag in the video compared to the actual video? Video, but the render, the location.
Maybe a slight lag. Like it could be like a.
Like on the wood router, it's it seems like we got the corner. It's hard to tell.
Yeah, this is a relatively old PC. I think it actually is Tormach inventory number like 120 or something like that. So it's an old PC, and it's got only a one USB 2.1 bus, and so we're pressing these. The reason these camera windows are so small is there's not a USB throughput with two cameras to show them at reasonable resolution, and so it does lag. The cameras lag slightly, if that's what your question is.
Yeah. Well, you're probably also doing a lot more Z-axis height control than you would on the router. You're even using more processing power just in the CNC, right?
Yeah, that's not taking too much, but you can see as an aside this up and down here when these buttons when these lights light up, that's when it's adjusting it's not exactly or whatever, but that's when it's going up and down on the torch. High control. The piece I passed around has a little edge. They have little edges on them. If we get this tuned, that means that our laser focus wasn't right. We literally didn't do anything with like the head height or the laser focus to get this tuned in, but these parts, when they do come off, if it's tuned in right, it'll be super cool on the edges. I was kind of encouraged that at least the dross was pretty consistent, which means we were holding a pretty consistent height, even though you could see it did go up and down about 0.06 inches over the course of that cut. But yeah, now the next steps, I don't know if I showed that part of the presentation for the Q&A, but so there's still some configuration to finish. We were manually controlling the laser power. We need to control it within LinuxCNC. That's all ready to go. It needs to be wired up. And then we need to figure out sort of the speed that feeds equivalent on the laser, which is like cut heights, pierce heights, the laser power, and the travel speed for tuning in, specific materials and thicknesses. And again, this is more kind of a test bed. I think it's a really cool machine in its own right. Even cooler would be a bigger version of this and more.
If we wanted to buy one of those lasers right now,
You can get a 750 watt laser in China for $900, which is insane. That used to be 20,000.
that's like $10,000.
Yeah, and I mean that you could literally buy a 10,000 watt fiber laser right now, and that's going to be many thousands. But
Your own private ophthalmologist.
what's that?
And your own private ophthalmologist.
Yes, yeah, exactly. All right,
Oh, it worked.
We're gonna put an op amp on that thing.
that's why I did the Ethernet control so that we can do exactly that. Yeah, okay, that's all I got.
Great, thank you, Mr. Scott.
Is the camera protected the, recording system?
All right, I think that's all we've got for the evening. I did grab Jeff brought in a 3D camera, but I can use it next month and show that thing off. We got a little handheld 3D scanner. Anybody else had anything they wanted to share, talk about otherwise? Yep.
I brought some trinkets here, the we got passed around, the lathe tools are here, if anybody wanna.
Cool. So Davey brought over all of his lathe show offs, and you're selling those for what, 1,000 a piece, 1,500? I mean, bargain. 25 bargain basement. Yeah. Buy a couple. I mean, you know, I think he'll give you a 30% off.
Pick up the machines, man.
Exactly. So Davey works for the manufacturer who makes all the machines, and so he helps. He needs to understand how they work in order to be able to talk to customers about how to use them. So a lot of this effort is in learning how the machines work for himself, so that he can talk to somebody about how they might be able to do something with it. But
So you're a troubleshooter or salesman?
Not
Yes.
efficient sales.
Okay. I'm efficient.
all right, Zoom folks, I'm gonna cut you guys off.